come to our example 2 on the Maxwell-Boltzmann distribution theory that we covered. It says a container of carbon dioxide, 10 moles, and temperature 300 Kelvin, and volume of 10 liters. So container contains 10 moles of carbon dioxide and has a temperature of 300 Kelvin and occupies a volume of 10 liters. So find the most probable speed, the average speed, the root mean square speed. What is the total number of carbon dioxide molecules in the container, and the value of the maximum. That means the number of particles in that gas that are moving at the most probable speed, right? The maximum value of the NV. What is the probability of finding a carbon dioxide molecule moving between 500 and 520 meters per second? Okay, so let's first find the V probable, and that's going to be equal to 2RT over M. 2 times 8.315. The temperature of the gas is going to be 300 Kelvin. The molar mass of carbon dioxide, oxygen is 16, multiply that by 2 is 32, and carbon is 12, that's 44. So that's 44 grams. Carbon dioxide has 44 grams per mole, so you change that to kilogram, 0.044. Okay, then you put that all into the calculator. That's the most probable speed, right? And then the average is going to be square root of 8RT over pi m, right? Well, if we don't want to do the RT over m again, you can just say, and you're going to get 2 over square root of pi, then you're going to get here 2RT over m, right? So what I did is I factored out 8 is equal to 4 times 2, and then that's equal to 8, right? The 2, I just kept it in the radical, and then that's going to be the 2RT over m, and then the square root of 4 came out as a 2, then I took the pi out, so this one is already the VP, right? 2 over radical pi VP. So I just multiply this number by 2 over rad pi. Multiply it by 2 divided by pi to the power half, and that's going to give you 379.96 meters per second. Okay, so what I did was I factored out the square root of 3 over 2. So now if I put this back into the radical, look what's going to happen. The 2 is going to go in there and cancel the 2, right? And then the 3 is going to go in there as a 3. So what I did is, because I wanted to write it as 2RT over n. So you just factor out the 2 on the bottom, which goes back in there and cancels that, and then the 3. So then this is a VP, so you have V root mean square root of 1.5 times VP. So then you just do whatever the VP you got, 336.73 times 1.5 to the power 0.5, and that gives you 412.41 meters per second. Down after that, so the root mean square speed is 412.41 meters per second, right? Okay, to find the number of molecules, we do the number of moles times Avogadro's constant. So this is 10 moles, and then Avogadro's constant says whenever you have 1 mole of anything, then you have 6.023 times 10 to the 23rd particles or molecules of that molecule. So in this case, we're talking about molecules of carbon dioxide. So we have here 1 mole of carbon dioxide has 6.023 times 10 to the 23 molecules of carbon dioxide. So you multiply that, you get 6.023 times 10 to the 24th. This is going to be molecules of carbon dioxide. So that is the number of molecules, right? So then in the equation, our equation for NV, is equal to, our equation was 4n over square root of pi VP, then you add V over VP squared, e to the minus V over VP squared, right? So then if I want to know the NV value for any speed, all I need to do is apply this. Now the way we define this n of the Boltzmann distribution function, this n was the number of molecules per unit volume. Okay, so it's not the traditional N that is the total number of molecules, but it is the molecules per unit volume. So then you take this one here, the 6.023 times 10 to the 24th molecules of carbon dioxide, right? Divided by the volume, which is 10 liters, and then you say 1,000 liters is 1 meter cubed. So the conversion between liter and a meter cubed is that 1,000 liters is 1 meter cubed. And then this will tell you what the N value is. So then you have here the 10 is going to cancel the 0, right? So this one cancels this, and then 100 goes up. So then you have here 6.023 times 10 to the 26 molecules per meter cubed. Okay, so that is the N value as described in that equation, right? 6.023 times 10 to the 26th. Okay, so then I'm gonna, if I want to find the NV value, it's going to be 4 times 6.023 times 10 to the 26th over square root of pi. Now I want to know the NV value exactly at the probable speed, right? So then VP, I'm just going to put whatever my VP was, right? Which was 336.73, right? V over VP is going to be just 1 because I'm already at the most probable speed. So V over VP is 1, and then you have here e to the minus, V over VP is 1, and then so e to the minus 1 squared, and then that's just going to give you that. So then you do as the units of the N. But 1.485, 10 to the 24th. So this is going to be the value here, 1.485, and then the peak here is times 10 to the 24th molecules. Remember, when I integrate this whole thing, what should it give me? When the integral of this, the integral of all this should give me the 6.023 times 10 to the 26 molecules per meter cubed. Then when I multiply that by the volume of the container, that should give me the total number of molecules of the carbon dioxide. So the integral of this is the N value, right? And then the N value multiplied by the volume of the container is the total number of molecules. And then so that's always the way that it should work. Okay? Now, if I wanted to know the NV value any other place, let's say the root mean square. How many particles are actually moving at the root mean square speed? How many particles are actually moving at the average speed? We can do that. All right? Remember, the V average was 2 over square root of pi times VP. Then you divide that by VP. So that's going to be the ratio, 2 over square root of pi. So then you have here NV, V equals V average, 4 times 6.023 times 10 to the 26th over square root of pi, 336.73. V average over VP is 2 over square root of pi, but then I'm going to square that. So if you square that, 2 over square root of pi, you're going to get 4 over pi. Right? Then you multiply this by 4 over pi. Then you're going to do e to the minus, and then the V over V average over VP squared, which is going to be the 4 over pi. Okay, so then basically you're multiplying this thing by 4 over pi, and then you're multiplying, raising e to the minus 4 over pi. Let's see what we get here. Okay, 1.439 times 10 to the 24th. So even though this makes it larger than the previous one, remember the other one was 1 here, but then this one counterbalances that, so it's instead of e to the minus 1, it's e to the minus 4 over pi. This one trumps that one, and this one should be a smaller value than this one, 1.485. We can take a ratio, NV, V equals V average, over NV, V equals VP. Or maybe let's put the bigger one on the top. The number of particles that are moving at the VP divided by the number of particles that are moving at the V average. So then it's going to be 1.485 divided by 1.439. So if you take the ratio of that, 1.485 divided by 1.439, it's going to be 1.032. Okay? So that means there is 3.2% more particles. If you change that to a percentage, 3.2%. So there's 3.2%, this is 3.2% higher than that, right? There's 3.2% for every 100 carbon dioxide molecules moving at the V average, there's 103 carbon dioxide molecules moving at the most probable, right? For every 100 molecules here, there is 103 molecules moving at the most probable. So you can, that's what it means to say the ratio is 1.032. There's a 3% higher likelihood of a molecule moving at the most probable speed than the average speed. So this one should actually be not as sharp like this. It should be just a plateau and slightly going down. Right? So this one, so now I'm going to do the, let's write this one down here. 1.439 times 10 to the 24. Now let's do the how many particles are moving at the root mean square. So then instead of square rooting it and then squaring it again. Right? So then I'm just going to do here 4 times 6.023 times 10 to the power 26 divided by pi to the power 0.5 divided by 336.73 times 1.5 times e to the power negative 1.5. And then you're going to get here 1.351 times 10 to the 24. 1.351. There the drop is a little bit more, 351. So it kind of comes down, starts to come down. 1.351 times 10 to the 24. So if I take the ratio, how many are moving at the probable versus divided by how many are moving at the root mean square. 1.485 over 1.351. 1.485 divided by 1.351. 1.099. Right? So then what's going to happen is that's 9.9%. So let's just approximate that, approximately 10% higher. Right? So for every 100 molecules of carbon dioxide that are actually moving at the root mean square speed, there's going to be 110 of them moving at the most probable speed. So for every 100 molecules here, there's 100 here. For every 100 molecules at the average speed, there's 103 there. Now the next question we can ask is, are these ratios constant? Are they true for any gas? In other words, is it always true no matter what the temperature, that the ratio of the number of particles moving at Vp to the number of particles moving at V average, is it 110, 100? And then the other one was 103, 100, right? Is that ratio the same? The answer is yes, because no matter what the Vp of the gas is, no matter what the temperature of the gas is, if you do NV at V equals Vp divided by NV, V equals V average, so then you're just going to have this 4n over square root of pi Vp, then you're just going to have e to the minus 1 divided by pi. So no matter what the Vp is, this is going to cancel, and then you're just going to get here Vp and what the temperature of the gas is. And then if we do this one, V equals Vp divided by NV, V equals V root mean square, and that's going to come out also, the 4n is going to cancel, so you just get 1 e to the minus 1 over, then you're going to get 1.5 e to the minus 1.5, so then you're going to get here 1 over 3 halves, e to the 1.5 minus 1, and then you're going to get 2/3 e to the 0.5. And then this is going to come out to be the 1.099, which is the 100-110 ratio. But now if I were to ask you a question, what's the ratio of the number of particles moving at a certain speed? Let's say, how many particles are moving at 500 meters per second? Find the ratio of the particles moving at 500 meters per second to Vp. Then at a certain speed, that depends on the temperature, right? So second, right? So then you have here Vp squared over, well, we could just do a ratio, invert this. So then you have here Vp over 500 squared e to the 500 over Vp squared minus 1, right? So the answer depends on what the Vp is, right? As the temperature of the gas increases, this thing shifts over to the right, because it starts looking like this, starts looking like that, then starts looking like that, right? So as the Vp is increasing, this number is getting larger, but then this number is getting smaller. So it depends on which one's winning which one. so that the ratio, when we do the ratio, see which one is bigger. Now, there might come a point where if I raise the temperature some point, the VP might actually become 500, right? That means then the ratio of this over this will just become 1, right? So when VP is 500, what will happen? This one will just be e to the 1 over minus 1, which is going to be e to the 0, which is going to be 1. And then when VP is 500, this is also 1. So that means there are the number of particles is already peaking at 500, right? When VP is less than 500, right? Then what happens is this ratio is smaller than 1, but this ratio is bigger than 1, right? So then it's peaking over here, and then what's happening is that the ratio, this number is going to be smaller than that, right? Then what happens if the temperature is greater and the VP is actually more than 500, right? If VP is more than 500, what should happen? So then, let's say it's peaking at 700, right? The ratio should still be larger than 1. So then what happens? The VP is greater than 500, so then this number is smaller than 1, right? VP over 500. If VP is greater than 500, so let's say VP is 700 squared, e to the, and then you're going to have 500 over 700 squared minus 1. So if the velocity is greater than 500, this number begins to get large, this number begins to get small, right? So let's just say what that number would be. Okay, so that means there's 20% more particles moving at 700 than 500 meters per second. So the peak is always going to be at V equals VP, no matter what the temperature is. But when the VP is 500, then the 500 will be the most likelihood, right? Okay, now let's answer the last question. The last question said, what is the likelihood, what is the probability in that container of finding a carbon dioxide molecule moving between 500 and 520, right? In other words, graphically what that means is to find the area under the graph, okay, go like this, find the area under the graph between 500 and 520. Find the area under this. And then divide that by the total number of particles per unit volume, right? So divide that by the n value. How many particles are moving between 5 and 520? The actual way to do this would be to integrate the function between 5 to 520, but we don't do it that way. Because the gap is very small, we can just take the midpoint of that, evaluate the NV value at a speed of 510. Take the midpoint and then multiply it by the interval. So we're doing it like the Riemann sum method. We're taking the midpoint method of the integral. We're calculating the NV value at 510 and then multiplying it by the interval delta V, which is going to be 20, right? So we're going to have here 4n over square root of pi. So then you're taking the value of the NV at 510, you're multiplying it by the thickness, dividing it by the n. So it's kind of a cheating way of doing this. Divided by n, integrate this, and then integrate it from 500 to 520. And then you're integrating this dv. Now the other way to do it is to say, okay, take the magnitude of the NV function at the value 510, which is the midpoint, and then just multiply it by the thickness and divide it by n. So then that's an easier way to do it when the interval is a kind of a small interval, right? Percent. In other words, the area under this graph constitutes 3% of the total area of that graph. That means there's 3% likelihood of finding a particle moving there. The likelihood of finding a particle here at the VP is going to be wider, right? What we could do if we wanted to do that is we could say, what's the likelihood of finding a particle moving at 336 plus or minus 10, right? Make the gap 20. Make this gap 20 meters per second. So then we would, what we would do is we would evaluate the constant NV at the 336, which is the highest peak, right? And then we would make an interval 10 meters per second to the right and then 10 meters per second to the left. An interval that's 20 meters per second wide. So we could say, what's the likelihood of finding a particle moving at the most probable speed with an uncertainty of 10 meters per second in either direction? That probability should be higher than 3.10%, right? So what would we do? We already know the value of the NV at the most probable, right? We would divide that by the N value, which was how many particles there are per unit volume in that gas overall, right? So it was 6.023 times 10 to the 26th. Okay, so let's see what this is the probability of finding a particle moving at the V probable with an uncertainty of 10 meters per second. 93%. So it's a higher probability. So this is going to be the highest probability. If we take any 20 meter per second interval, that's the highest probability. So there's almost 5% chance of finding a particle, right? This is 4.93%. 5% chance of finding a particle moving at the V average versus over here, it is a 3.1% chance, okay? So now you can see a good example illustrating all the possible different kinds of questions that can be asked and analyzed from the Maxwell-Boltzmann distribution of gases, okay? Thank you very much.